Oh, thank you very much for the introduction. So actually, I should start to thank the organizers, in particular Irina, who is not here, and Erland, who is here, for trying to invite me already several times, but it was always cancelled by COVID or some other things. And this time it went through, so I'm really happy to be again in Bergen. And I wasn't completely sure about what to talk about, and so please, because the topic will be not really inside of the mainstream, perhaps here in the audience, for the people, don't hesitate to stop me and pose questions. It doesn't matter if I don't go through everything I prepared. It's much better if you get at least some message from the talks. And what I will work is geometries, which look sort of strange, because what does it mean, parabolic geometries? You will get a message, but actually the aim of the talk is to convince you that actually it's quite good to understand even very usual objects like obvious, usual linear connection as what we would call rather affine connection, and in view of, and if you view it as the collection of the soldering form and the connection form, so you rather view the connection as something sitting on the frame bundle than on the manifold. So the frame bundle for me is the bundle of all the frames for the tangent space, right? Then together with the fact that all the objects like the fields used in physics or elsewhere are coming from some representation of the structure grouping question, either orthogonal, Riemannian, or some other one. And it's just you view your objects as equivariant mappings from basis into coordinates. So it's definitely not the way how you would explain what a vector space is for the freshmen in the first semester linear algebra, but it's definitely something they should hear sooner or later and understand, because that's the core, right? And that's the core of the approach of Cartan and other masters, and that's behind what we call Cartan geometry. So all what I will be talking about is about Cartan geometries, and it will cover geometries and calculi you basically definitely already know. It's just showing them in different picture, and I very much believe that the calculus which is behind can be very useful in general. I will come to some further motivating explanations, I hope, later. So, of course, this is something I should go back in history, because as I mentioned already, so this is the approach which could be tracked back to Cartan and his predecessors. So it's something like, I don't know, maybe back to Felix Klein and Bernhard Riemann. So it's something like 150 years old history at least. But I will leave out the main motivation for our team, which was the group around Roger Penrose and the complexified version of the gravity theory, where the conformal geometry plays the crucial role. And they wanted to understand the invariants, and they wanted to know how they work. And the way out for us was to understand them very much in terms of pure algebra, Lie theory of the Lie algebras, Lie groups, etc. And for me, in the beginning of 90s, or in the middle of 90s, there was this paper by Paul Goduchon structure about the so-called Weyl structures, which deals with Weyl connections for conformal geometry. So all the connections where the holonomy sits in the conformal orthogonal group, and that's it, right? And it's known that they are containing all the Levi-Civita connections of the conformal class of the metrics. And it's known that there are some more. And that was of big interest in the time of Hermann Weyl, because it was one of the beliefs of his and Einstein's that the antisymmetric part of the Ricci curvature for those who are not coming from a metric but are in the conformal class would help with unifying the gravity with other theories, right? So, and Paul Goduchon just approached the things exactly as I will do in the future. And there was a series of papers of my collaborators, Andreas Cap and Vladimir Souček from Vienna and Prague. And we first wanted to understand the conformal structures. That was our goal. So conformal Riemannian structures, how to build a calculus. So the people around Penrose, would simply write out the formulae for the invariant operators and these kind of differential invariants. And they were absolutely happy to see what they call miraculous canceling. So you compute, you fill about 7-8 sheets of paper by horrible formulae, and in the end, all the bad terms cancel each other, and then you see, yes, it's invariant. And I hated that because I'm not able to compute this well, so it was completely unbearable for me. So I decided, and Andreas Cap and Vladimir Souček joined, and we worked together. We decided to restrict ourselves to similar Lie algebra setups as the conformal or projective geometry, and to try to do it in a completely algebraic way. And there was a series of papers. You see 1, 2, 3, and then we were heading at the 4th one. And until we came there, we understood that what we were doing works actually for all the cases of what I will call parabolic geometry. So the 4th one is no more 4th one, but a new one. And you see, we were quite lucky and successful and solved it in Annals of Mathematics. So that was a big achievement, and we were going further. So this is another algebraic background I will come to, and then finally we were invited to write the first monograph on the subject, which we asked to be split in 2 parts. And the first part appeared in 2009, and the second one essentially hasn't been started yet. And what I will be today talking about is a beginning of the second part. So, and it's also, well, I mean, we knew the content of what I will be talking about already something like 15 years back, but we never finished that, and we came back to that after Andreas found out some new observations and thoughts about what we call Weyl structures, and this appeared very recently, so it's just already online, but not yet having the number, and I will continue with that. So, on my first slide, I would like to remind you more carefully about what does it mean to have a conformal Riemannian manifold or a projective manifold. That's the other one. So I guess everybody in the public knows what's that. So simply you can view the conformal Riemannian manifold as something where you have got a Riemannian manifold. You just forget about which one of the connections, which one of the metrics is there, and you instead consider a whole class of them which are changed by multiplication with a positive function, right? Another point of view is it's a classical G structure, so you start with the frame bundle of the tangent bundle and reduce the structure group from GLN to CSON. So the orthogonal group plus the dilations, right? So you can just rescale the units. And in terms of algebra, what you find is you simply work with a bigger group. So this big group is actually SO P plus 1 Q plus 1, right? I tell Riemannian, but I mean pseudo-Riemannian in general. So PQ is the signature, right? And so this big group, so is there a marker? So that will be very unfair to those online, but you can imagine you have simply a bigger group and the structure, so it's like a subgroup in GLN or well, rather algebra GLN, right? And the sizes are 1 and 1, this is P plus Q, it's N and the same here, and 1, and then you can see it's SO P plus 1 Q plus 1, or it could be, say, SU P plus 1 Q plus 1, or it could be SP P plus 1 Q plus 1, and you will get the conformal Riemannian or the CR geometries. We heard about them today already, or this will be the quaternionic contact geometry, so codimension 3 distributions, and it will be quaternionic matrices then, yeah? So just to have an idea what kind of algebra is in the background. So you usually have something like a matrix algebra, and you get some grading of the algebra as here. So this should be G minus 1, not G minus only, right? G minus 1 here, G0, G1, that's a grading of the algebra. And here it would be, this is G minus 1, this is G1, G plus 1, and here is the G0. And here on the other ones, on the other sides, this is just computed from the antisymmetry of the matrix, right? So it will be antisymmetric if we go for the SO. It will be antisymmetric with respect to the given signature. And if you go to the CR, it's suddenly something like anti-Hermitian. So here you see its imaginary contribution. If you go to the SP, it's again quaternionic Hermitian antisymmetric, so you would get three-dimensional imaginary contributions in the corners. So only the conformal one is one-graded in the sense that it starts in G minus 1 and ends in G plus 1. And the projective structures are something similar, except it would be just another picture. It would be just the whole of GL n plus 1R, and the structure would be this, G minus 1, G plus 1, and this is just the G0. So the conformal ones are given by a choice of a class of metrics. The projective ones are not. There you have to choose a class of connections already. And the connections are sharing the geodesics. So you simply pick up one connection and say that all other connections sharing the same geodesics would be in the class. And in both cases, you can notice the similarity that they are both parameterized by one form. So the freedom in the choice of the connections is always just an affine space modeled over one form, right? So now we come to a more general definition which covers those two cases, and that's what the Cartan connections are. So if we start in the setup of a homogeneous space, so we are in the setup of Felix Klein, so the Erlangen program. So we have a pre-group G, a closed subgroup P, and we consider the manifold M, which is G mod P. And then, of course, G over G mod P is a principal fiber bundle with structure group P, and there is the Masaryk-Cartan form omega. And if you, for example, would start with a affine group, the GLN as the subgroup, and the standard Masaryk-Cartan form of that matrix group, then you can just explain that to your freshmen enrolled in the elementary analysis course and build all the analysis on Rn this way for free, because the canonical connection there coming from that would be just the partial derivatives and all the things like that, right? So everything would be there. And the Cartan geometry it's a curved version of the same thing. So instead of the Masaryk-Cartan form, you simply consider a similar form, omega, having also values in the same real algebra G, which is the model space, or the model algebra. But G, the curly G, is now a general principal fiber bundle with the structure group P, and you want omega to enjoy all the properties of the Masaryk-Cartan form which still make sense. So you want that along the fibers, the absolute parallelism should reconstruct the fundamental vector field. So the fundamental vector fields along the fibers on a principal fiber bundle are the same thing as left invariant vector fields on the homogeneous model, just restricted to the vertical directions, right? So that's this requirement. It reproduces the fundamental vector field. But then it has to be right equivariant with respect to the adjoint representation. That's what's true for the Masaryk-Cartan form. I mean, the left invariant vector fields are obtained right actions and computing the things. And if you just do the computation, you get this formula. But of course, here it's not working for all the group elements, but only for B in P, right? Because it doesn't make sense otherwise. So you have to consider only the right action. And the third one is that it's a linear isomorphism. So this is the concept how to generalize what happens in the Felix-Klein's homogeneous space, having the Masaryk-Cartan form, therefore free always to have the curved version. And for example, if you start with the affine group, then what you get out of this type of Cartan geometries, due to the reductive structure of the affine group, it's a direct product of Rn and GLN, right? You get exactly the linear connections, nothing but that, except the omega splits into two parts. One is the soldering form, which identifies the principal G bundle with the linear frame bundle of the tangent space, and the other part is the connection form. So that's it. Of course, what you get as an extra object is what you obtain if you write down the structure equations, because for Masaryk-Cartan form, this right-hand side gives you always 0. Whereas in general, for the Cartan geometry, this will be what's called curvature of the Cartan connection. Again, if you write it for the affine connections, which is just the affine group model Cartan connections, you will have this curvature split because it's all reductive into the Rn part and the GLN part, and that will be exactly the torsion and the curvature of the curvature, right? Whereas here we have packed it all together. And in geometries like, say, conformal geometry, the main problem is that the big structure group, this one, is not reductive, because if you act with the elements from G1, you move from G minus 1 to G0, etc., right? So only the filtrations have make sense there. But not the ends. So you can start with G1. This is a well-defined subspace, right? P invariant. You can take G0 plus G1, but you can't say, for example, G minus 1 component would make sense by itself. And of course, just having all that from the previous slide, we know that omega defines constant vector fields. So that's the inverse images or fixed constant value in the Lie algebra. That's what would be the left invariant vector fields in the homogeneous model. Now we have something similar in general. The right equivariance says how the constant vector fields behave, and curvature descends down to a curvature function, which in the sense I talked about the vectors being the mappings from frames into coordinates. So this kind of curvature means that you have actually some object which is living as a 2 form on the manifold downstairs, but is valued in something which I will call adjoint vectors in a moment. And curvature is a horizontal 2 form. Now, what are the parabolic geometries? So I come to the beginning of explanation of what the title means. So not very good in the half of my time. So parabolic geometries are simply the Cartan geometries with special choices. You can take any semi-simple E group G and any parabolic subgroup P. Parabolic subgroup is any subgroup which contains Borel subgroup. So it has got a nice equivalent definition in the complex setup. So you can say that a complex subgroup in a complex semi-simple G is parabolic if and only if G mod P is compact. And for the real ones, it's the same as having the complex one parabolic, right? So if I draw it in this kind of block matrix form, then it means it always has to contain the upper triangular subalgebra completely, and then it's parabolic, right? So the morphisms are as I say, and the nice thing is that from the representation theory, you know that whenever you have such a choice, parabolic P in semi-simple real G, that at the level of the Lie algebras, you always have this very symmetric grading. It always goes from minus K to plus K. Here you have something which shows you how the tangent space would look like. Here you see it's the dual to the tangent space with respect to the Cartan killing form. And here this is the reduction of the endomorphisms of the tangent space, which in particular will preserve the filtration, which we come to in a second. And the notation is that just the non-negative part of the grading is called P, and it's the Lie algebra of the P. The positive part of the grading will be called P plus, and the negative part will be G minus. Yes, that's what I'm writing here. So P plus is the nil radical in the parabolic subgroup decomposition, whereas G0 is always the radical, is always the reductive quotient. But in our setup, we have chosen already the embedding of G0 into the P, which is in all cases, again by the representation theory, uniquely available up to conjugation. So you could conjugate everything, then you get the G0 sitting slightly different there, but all the theory would be same. So it's something like, so this particular choice in the theory is something like, perhaps everybody thinks that if you build Riemannian geometry, it's a good idea to choose and fix your scale on Rn, and then to consider simply everything being like that. Whereas if you would be very Puritan, you shouldn't, and then it explains why the Levi-Civita connection remains the same if you constantly rescale your metric. Right? So that's the reason that there was this freedom. Once you fix it, algebraically everything is fine, and you get the unique Levi-Civita connection and everything, but in general you shouldn't. So here it's something similar, and of course because P plus is the nilpotent radical, so it's the exponential image of P plus, and the same G minus would be the exponential image of G minus, and for the elements in P, we always have a unique decomposition of this kind, or we just write it as G0 times X upsilon. So upsilons will be for us all those things from P plus, and they sort of show us how we move in the fibers in the direction which is already outside of the radical part, or of the reductive part of the parabolic subgroup. And last but not least, as soon as we fix the position of G0 inside of P, we get a uniquely defined so-called grading element. And the grading element is exactly the element which, by the adjoint action, tells you the splitting into the grading, right? And it's equivalent. If you choose your E and say this is my grading element, it just gives you one of the choices for the G0. So now we come to the main special thing which mimics very well what's happening in the conformal geometry and projective geometry, and that's the Weyl structures. So as I already stressed so much, spending so much time on that, if I fix my favorite parabolic subgroup P, then the subgroup P splits into semi-direct product of the reductive part and the nil radical, right? And that's always the case. So in the say conformal geometry, the reductive part is just this blockwise diagonal, and the nil radical is the G1, right? So X of G1. In the projective case, again, this is the reductive part, this would be the nil radical, right? And you can see it quite easily. But then, if I get a Cartan connection on such a principal fiber bundle, then of course I can be interested what happens if I reduce my structure group to the reductive part, which is exactly like choosing one of the Weyl connections in the most standard conformal geometry, right? What Hermann Weyl was doing. And as soon as you do it, you simply pull down, or pull back, actually, but it's going, so I always draw it. G is up and G0 is a little bit lower. So you simply pull back the connection form omega. So you have the omega is sitting on G, and you reduce the structure group to G0. So G0 is embedded into G, so you can pull back all the components. And now, because we have got only G0 structure group, which is the reductive part, so the components are already invariant, right? It's well defined. Once I reduce the structure group, it's well defined. So I get separately the soldering form, which will be something which tells me in which sense the tangent bundle is given as the graded Lie algebra. Actually, not the tangent bundle, because on the tangent bundle I inherit the filtration. So G minus 1 gives me a distribution. Usually you call it E or H in sub-Riemannian geometry. And then the rest is bracket generated from the G minus 1, because this is always the case. This is nilpotent bracket generated. So up to a choice of metric on the G minus 1 is exactly what you are used to call Carnot algebra, right? So this is telling us the reduction of the reduction of the structure group to G0 is first of all telling us how the filtration done by the bracket generating, exactly the way you are used to, how this filtration breaks into grading, right? And of course, the way how it breaks into grading depends on which reduction I change. If I move with the P plus entry, then it will reshuffle the components there. Again, something you definitely know from sub-Riemannian geometry. If you change simply the components, everything changes. So this is, so then the next one is the component in G0. And this is just a connection form. So it's a linear connection form. And the third one, rho S, is something like a measure, so a tool measuring what's the difference between the things. So you see theta is a soldering form on M, which identifies Tm with graded Tm. Gamma is a linear, gamma is a linear connection on M. So if I sum them together, theta plus gamma, then I get what I call affine connection, right? And rho is a one form on N valued in T star N, in G1. G1 is there to model the T star. And it just measures the difference between the original form omega and theta plus gamma on the image, right? So now what are the natural bundles? So the natural bundles come from every representation. So whenever I take a representation lambda on a vector space, so I'm in a P representation, then on the homogeneous space, I get the so-called homogeneous vector bundles. I associate the standard fiber to G. But more generally, I get the same for every Cartan geometry, right? And for that construction, I don't need the omega, but the omega is useful to identify things. For example, the tangent bundle will be the Vm coming where the blackboard bone V will be just the G minus 1 is the P action obtained by truncating. So it will be just the action mod P, right? So I view G minus as G mod P. So this is what I call natural bundles, and there is a special class of them called tractor bundles. The tractor bundles are special because each Cartan connection on the big principal fiber bundle extends to a principal fiber connection on the extension of the bundle to the whole G. That's a tautological construction, and therefore, if we deal with special modules which come as P modules through restricting the G module action, then for sure we will always get linear connections for free. That's very good. And particular occurrence is if we take the adjoint representation on the Lie algebra G, and this is what we call the adjoint vector bundles. And for example, the curvature is a two-form on the manifold valued in the adjoint vector bundle. Now, let's go one step further, and that's the observation done by Andreas and Thomas recently. Simply, you can again observe that there is the tautological construction known for forever, that if you talk about reductions, then it's the same like having functions of the relevant quotient. But in our special algebraic setup, this quotient is actually the same as this. And it's therefore a very nice affine bundle, not vector bundle, but affine bundle, modeled over one forms. And we get, in general, that not only the Weyl structures always exist, but also that they are always modeled by one form, just like with the projective and conformal case. For all the universe of the choices of semi-simple and parabolic subgroups. And moreover, of course, whenever we get a p-equivariant mapping, sigma, that will be a section of the natural bundle, then of course I can compose it, and I will get a representation of that section on G0. And this will split into the components by the same by the same action of the grading element, etc. And most notably is the following fact. Worth mentioning, because you see omega, I just reshuffle the components. I write omega minus, then omega plus, and omega 0. And you see, over the bundle A, this is a G0 principal fiber bundle. And because it's a G0 principal fiber bundle, these three components make sense. And the whole omega is nothing but a regular, normal, usual, nice affine connection on the manifold A, where omega minus plus omega plus play now the role of the soldering form, and the omega 0 is the connection form. Right, and on top of that, just by the Lie algebra structure, the tangent space to A splits into L minus and L plus, which corresponds to the G minus and G plus. And there is P, so rho, which is the projection to the vertical bundle with respect to P, that's the L plus, along the L minus. The torsion will be also split into two components, T and Y, and there will be some curvature, W. And we shall write for each choice of the Weyl structures, we shall indicate the corresponding objects with an S here. Oh, I'm getting short in time. So now it will go faster, because we've got the bundle of Weyl structure, that is the A, and you see that the sections of the natural bundle over M are always sitting inside of the natural bundle over A, because every P equivariant mapping into the coordinates is in particular G0 equivariant, right, by restriction. So there is no problem. So whenever I have an operator, then which is written in terms of the linear connection omega on A, I can restrict it to sections from the natural bundle over M and try to have a look how this expresses in terms of the Weyl connection, right? So I have something which naturally exists upstairs. So whenever you have got an affine connection, you know that all the differential invariants can be written down with respect to the covariant, with the help of covariant derivative and curvature, etc., right? And now we do the following. So once we choose so I will go back. So here I have just the setup upstairs. So I have the sigma. This is the value on sigma. I can write the same here in terms of the equivariant functions. And once I fix my reduction, I get the graded versions of the bundles downstairs. I get the induced graded version of the section S, a sigma, which corresponds to the composition here. And composition that with that. And then I can also do the same with the operator. So here is the operator upstairs on the A. I restrict it to the sections on M downstairs. And I get I should get something here, right? And I would like to write this down in terms of the Weyl connection and the curvatures and things I've got there. And that's something we can do, because actually once we want to restrict it here, so what we do is we restrict the covariant derivative with respect to omega on the bundle of Weyl structure, so on the A, only to L minus, because L minus is the realization of the tangent space upstairs. So we do that, and we shall write this for that. And this comes nicely, and we arrive at the first theorem saying that actually, well, I should explain, so this rho corrected derivative means that I take the covariant derivative with respect to the Weyl connection, and this is an algebraic action of the value of the pullback of rho. So it has values in G1, and G1 acts, it's a P plus thing, so it acts on my section, right? If the section would be from irreducible bundle, then it would be just not existing. So, and the claim is that for each operator, I can just rewrite it completely in the terms of the Weyl connections, the curvature of the original connection omega, and the rho's. So, if I start with irreducible, you see that, for example, the second differential is already quite complicated thing. Now I'm coming close in my last 3 minutes, or how many? So that's not very, very good. So, of course, we would like to mimic the approach from conformal or projective geometry. So we would think that the invariants, which are interesting, are written down with the help of the Weyl connections, and they result in expressions which do not depend on our choice, right? That's how the people in gravity always worked. And therefore, if we change the Weyl structure, we have the freedom in P plus, so that's the Upsilons. We want to see how the Weyl connections and the splitting and everything is changing. And you see, the formulae are horrible, so I will just go through without telling how much horrible, but they are horrible. And even in the one-graded case, for example, the conformal one, they look horrible enough, right? And in particular, you see that if you differentiate the first line again, then there will be a derivative of Upsilon. And you see that the transformation of rho shows up with the same derivative of Upsilon. That was exactly the observation which led, say, 100 years back to the creation of the Schouten rho tensor, which is a trace-adjusted Ricci. Now, I will skip this just by a short mentioning that, of course, we are not interested in geometries in terms of Cartan connections on some abstract bundles. So the people want to live with something which is on the manifold. And that's exactly here, and that's the motivation why perhaps in the future, even in sub-Riemannian geometry, this will become interesting, because actually what happens is that if you look in particular in the low dimensional and codimensional distributions, say something up to until the total dimension 10, then it's remarkable how many of them happen to be parabolic geometries, either in general position or in some of open cases, right? And so you see something like the gross vectors 2, 3, 5, 3, 6, 4, 10, and many other geometries are of that kind. So in some sense, if you have a sub-Riemannian geometry of this particular kind, then forgetting about the metric, you have a very rich geometry in the background, which is there, including curvatures, including a lot of things, which should be useful with technology of operators, etc. And And the point is that in most of the cases, it's just the filtration itself which gives you the complete geometry. It's only the one-graded cases which you have, where you have no filtration, no distribution at all, or the contact cases, which is infinite type geometry, where you have to shrink your G0 from GLE to something smaller. In most cases, you don't. It's everything hidden in the filtration itself. And now I will very quickly come to the punchline, because this is now straightforward. So actually, I could more or less jump to the very last but one slide if I look at the watch, but I try to tell a little bit more if you allow. So the covariant derivative can be written as for affine connections, is usually written as or can be written as the derivative with respect to the constant vector field of the coordinate function. That's it, right? And this is a particular good way how to write it down if you want to iterate the things. And this is exactly what it is. I mean, we can just write the covariant derivative for our connection omega on A this way, right? The point is that if we start with something P equivariant, we still most probably land with something which is only G0 equivariant. So it will no more transform sections into sections over the manifold M. But still, it's a very nice operation which is possibly iterated, and it could be extended to something I don't have to mention here, which makes sense always. And now the point is that for the first jet, so if you take the first jet prolongation of the section, so if we want to deal with first order differential operator, that's what we do, then you can identify the jet prolongation of our natural bundles with the associated bundles to this representation. So this works fine, and therefore, the invariant derivative composed with any G0 invariant map will give you something, right? And this is the way how all the first order operators are built very easily, even for all the parabolic geometries. So that's an easy task. With higher orders, it's more difficult, because we could do, say, iterative procedure to take jets of jets, and then take the equalizer of the many projections and land with something which is called semi-holonomic jets. And there it's again true, but it's not true for regular jets. So for regular jets, it doesn't work. And that's the difficulty in constructing the invariants for conformal, projective, and all other. So you have got, in general, you have got always, now I'm talking about absolutely general Cartan connections. You have got Bianchi and Ricci in this very general way, and it's even easier to prove them than what you see in the textbooks for the affine cases. And if we go back to the parabolic geometries, we can easily compare the curvatures. I will not go into the details. And then in the end of the day, we want to compare, say, affine derivatives, affine invariants, which are limited to L minus. That's the first line in the diagram. We reduce and we want to write the things down in terms of the connection downstairs. And we would like to see that it can be rewritten in terms of some affine invariant downstairs. And this should be the right thing. And actually it's the case. And the expansion I was talking about before is of this kind. So we can always find the psi, which is the universal expansion of our guy, which we chose above as an arbitrary thing. And now I am at my last slide. And the main theorem says that whenever you take a differential invariant of the Weyl connections and the row tensors, which you construct by the expansion from something from the Weyl bundle, then you get special type of operator downstairs, which transforms only algebraically in the Upsilon, which is just a miracle, right? Because if you remember how horrible the transformation formulae were, so it means that the rows are set in a very smart way to cancel all the differential dependence in the transformation. It's absolute miracle. And it's the reason for the miraculous canceling I talked about in the beginning. And the second part is even more surprising, because it says that actually every affine invariant in terms of the Weyl connections and row tensors, which does transform algebraically, comes this way. And that's the end of my story. So this is the what we call nearly invariant calculus, because you can simply set up an ansatz of all operators, say, of given homogeneity, which would transform only algebraically. And then, of course, those which are invariant are those where the result, what you get, is not only G0 invariant, but P equivariant. So, you see, I knew I would be too late.